Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. So let's try to recall what we were doing in our third SRAM module. First, we started by understanding what is the basic structure of your SRAM cell. We saw that it consisted in its heart of this cross-coupled inverter, and this cross-coupled inverter gave you a butterfly-like hysteresis loop, and the regenerative feedback arising from the butterfly hysteresis loop was the reason for having a memory effect. Also, in the end of last session, we saw the basic operation of hold, where whatever value is stored in nodes N1 and N2, you just want to retain it. So the philosophy is very simple. You decouple PG1 and PG2, which are your pass gate or access transistors, from your bitline and bitline bar, and this you do by deasserting the word line and keeping the bit lines in floating. Why you kept bit line in floating was very simple. You want to prevent any subthreshold leakage. In today's session, we will start looking at one of the most important fundamental operations of the SRAM cell, which is the read operation. In the read operation, just a quick recap of the SRAM cell. This is a 6T SRAM cell where you have a cross-coupled inverter. Since you have two inverters, you will have one pull-up and pull-down transistor each, as you see PU1, PD1, PU2, PD2. These are corresponding to inverter 1 and 2. As you can see, the output of inverter 1 is connected to the input of inverter 2, and the output of inverter 2 is connected to the inverter, the input of inverter 1. And of course, we have the pass gate transistors whose gate is controlled by the word line, and the ends of the pass gate transistors are connected to bitline and bitline bar. Therefore, bitline has access to storage node N1, and bitline bar has access to storage node 2. So in this structure or in this setup, let us assume that we have 0 which is written in storage node 1, as I have indicated, and 1 which is written in storage node 2. There is no need to again explain that this SRAM cell, although is a bit complicated, is storing only one bit of information, because storage node 1 will always be the complement of storage node 2. So in this case, in storage node 1 we have 0, and in storage node 2 therefore we have the value stored 1. So this is the setup. What is our objective? Our objective is to read the state of this particular memory. Let us assume that we want to read that the value, what is the value in storage node 1. So if we know that the value in storage node 1 is 0, it is obvious that in storage node 2 is just the complement. So the ideal objective will be to somehow read that once you turn on the pass gate transistors PG1 and PG2, bitline should reflect the value of 0 and bitline bar should reflect the value of 1. This is ideal condition. This is the expectation. We will see that this will not really happen. Something more subtle is going to happen. And if you recall our discussion when we were looking at sense amplifier design or memory architecture design, we realized that the bitline and bitline bar is not just passing through the source of one of these SRAM cells pass gate transistor. There are a series of SRAM cells connected to the bitline in a column-wise fashion, right? In a row-wise fashion. Therefore, it is not possible that whatever the entire value of node 1 will be reflected on bitline. That will take a lot of time, because the capacitance of bitline, CBL, will be much larger than the capacitance of this small tiny individual SRAM cell, right? This is because this bitline is running across so many SRAM cells which are arranged in a row-wise fashion. This context is very important before we move ahead. So although we will not be able to see bitline equal to 0 and bitline bar equal to 1, as we had also discussed, there will be a small analog voltage which will develop. It is but natural to expect that the ends of bitline and bitline bar will ultimately be connected to the two inverting and non-inverting inputs of a sense amplifier. So with this context, let us see how this read operation is facilitated. But there's a very important point which we should mention over here, that all of this read operation should happen without altering the value at N1 and N2. Without altering value of N1 and N2, and that by definition is called non-destructive read. This is called non-destructive read. What is the meaning of non-destructive read? That we somehow come to know what are the values at internode node N1 and N2 without disturbing the value at N1 and N2. Okay, here this is the particular context. Okay, so first and foremost, the only things that are under our control when we do any operation, like we saw from the hold operation also, is what are the voltages that we assert on word line, bit line and bitline bar. These are the only three things that we can control. So let us now try to intelligently evaluate what is the values that we need to assert on bitline, bitline bar and word line. Now the value for word line is very, very obvious, right? In hold operation, you wanted N1 to be decoupled from bitline. Here it is exactly the opposite. Here you want to read out some information from N1 and N2 on bitline and bitline bar. So it is but obvious that you have to assert the word line. And that is what I have done. I have shown that the word line, the read operation begins when you assert the word line from 0 to 1. What will the asserting of the word line do when you go do it from 0 to 1 or from 0 to VDD? Note, I will use 1 and VDD sometimes interchangeably. VDD is your analog voltage, 1 is your digital state, just to be very clear. So when you assert this word line, it is obvious that the pass gate 1 and pass gate 2 will get turned on. Okay, this is the first thing which is obvious. We have to turn on the word line. But before that, we have to determine what is the voltage at bitline and bitline bar. And the first thing that we do is we pre-charge the value of bitline and bitline bar to VDD. So what we do even before we turn on the word line, and that is why the terminology pre is coming here. I hope you remember why we use the terminology charge, because here bitline and bitline bar are these long interconnects with CBL as the capacitance. Okay, this capacitance will consist of two capacitances. The constituent capacitance will be one, the capacitance of the line, and also CGD of the pass gate transistors. So there will be also an associated capacitance which is between the gate and the drain or source of the pass gate transistors. Both CGD and C line will constitute of CBL, bit line. Okay, so the bit line will have a finite capacitance, and therefore the terminology charge, we are going to charge the bit line and bit line bar to VDD, and the terminology pre-charge comes from the fact that we have to do this before you turn on the word line, right? And please recall what was the structure of your pre-charge circuitry. We also studied that when we were looking at peripheral design. The structure of your pre-charge facility or your circuit was 3 PMOSs. One PMOS which connects VDD to bit line, another PMOS which connects VDD to bit line bar, and another PMOS which connected the bit line with bit line bar to equalize the potential, right? This is all that we have studied in our previous sessions. Okay, so first you pre-charge bit line to bit line bar, bit line and bit line bar to VDD or 1, and next you do then next you turn on the word line. This is what you essentially do. So before you turn on the word line, an important thing to recognize is when the moment you turn on word line, how do you do a simple circuit analysis of this rather complicated 6T cell. It may look that this is a very complicated structure with 6 transistors and many voltages flying around. So how do we simplify the analysis of read operation of the single SRAM cell? And the way to do that is, the first step is to recognize the fact that when your storage nodes are at stable values, in this case N1 is at 0 and N2 is at 1, only one of the pull-up or pull-down transistors each in the 2 inverters will be functional. We have to recognize that. Why is this the case? This is because look at first inverter 1. Look at the pull-up 1 and pull-down transistor. What is it connected to? It is connected to storage node 2. The value at storage node 2 is 1. As a result, the pull-up transistor, which is a PMOS, will be off or it will be deactivated. Okay. Similarly, since the pull up 2 and pull down 2 corresponding to inverter 2, the input is connected to storage node 1, the NMOS or the pull down transistor 2 will be deactivated, right? So right at the beginning, we can take out 2 of the transistors of this complicated 6T cell out of question, right? So in this structure where N1 has 0, N2 has 1, pull up 1 and pull down 2 will be deactivated or will be in off state, or there will be no activity at the beginning as such in pull up 1 and pull down 2 transistors. So it's very simple. From 6 transistors, we have eliminated 2 transistors. We are left at 4 transistors, and we are going to further simplify the analysis. How do we do that? It is important to recognize what is common now between both the branches, the left branch or the right branch. You can call it the left or right branch, or the branch connected to bitline and bitline bar. What is common is this pass gate transistors. So let us one by one look at what is happening in pass gate transistor 1 and pass gate transistor 2. And it is easier to first look at what happens in pass gate transistor 2. Now this image is becoming a bit more messy, so I have removed the pull down transistor, which is not very important as we just discussed, and just redrawn the schematic for pull up 2 and pass gate 2 transistor. So this is a more cleaner image. See, this is the pull up 2 transistor and this is the PG2 transistor. What do we see? Let us look and evaluate what are the voltages at different nodes of this connected transistor pair. We see that VDD is connected to the drain of the PU2, and at the source is also VDD. What is happening at PG2? The source and drain both have VDD. Okay, and although PG2 seems to be turned on because at the gate you have applied, which is connected to the word line, you have applied VDD, this transistor will actually be off. Why is this the case? Because look at the turn on condition of a transistor. It says that VGS or VG minus VS should be greater than VTH. It should be greater than VTH for PG2 to be on. But let us look what is the value of VG minus VS. We see that both at VG the value is VDD, and VS also at both ends the value is VDD. So VGS or VG minus VS is actually 0. And since this is less than VTH, which will be a finite positive quantity for a NMOS transistor, we can conclude that even PG2 is off. And since PG2 is also off, we can conclude that even the right hand side of the branch, or the branch which is connected to the bit line bar, will not facilitate the initial stage of a read operation. So see, our problem has become even simpler. First, we saw why PU1 and PD2 will not be operational because of the values to its inputs. Now, because of this condition, VGS less than VTH, we will see even the right hand side of the branch, which is PU2 and PG2, will not be operational. Okay, so out of the 6T, we have eliminated 4 transistors where the initial read operation can begin from. So what is the remaining part? It is the left hand side of the circuit which is connected to PG1. And this I have again redrawn a bit more neatly because this is getting a bit more complicated. Let's look at the internal voltage nodes at each and every point of this coupled transistor pair. What are the coupled transistor pair? You have PG1 and you have PD1. So here the bit line or the drain is of the PG1 is VDD. Internal node is 0. Right? The internal node is 0. What is at the word line or the gate of the transistor? It is VDD. So here VGS is VDD minus 0 is much greater than VTH, and therefore the NMOS over here, which is the PG1 NMOS, will turn on. Therefore, a read current will flow from the bit line into the storage node. Okay, so now we see where the activity in read cycle will be initiated from through this read current, the I read current. Okay, repeat, we saw that PG1 will indeed be turned on because it is meeting the condition VGS is greater than VTH. Here VGS is VDD minus 0, okay, which is greater than VTH. What will happen as a result? Please recognize, if a read current has to pass through it, we need to carefully look at what is happening at PD1, which is also an NMOS. What is happening at PD1? The PD1, the source and drain both are connected to 0. If a read current flows through it, of course that is not possible. If a current flows through it, there has to be a potential difference. There has to be a potential difference between VN1 and the ground which is connected to the source of PD1. There has to be a potential difference. And this is what shows up as a plus delta V dash. A plus delta V dash, a small voltage appears on the drain of this transistor. Otherwise, a current cannot flow through it, right? As we know, current cannot flow without a finite potential difference. And since a voltage develops plus delta V dash on the internal storage node, where will this current come from? This current will come from the discharging of your bit line. And therefore, your bit line, which was earlier pre-charged to VDD, will now get slightly discharged to VDD minus delta. VDD minus delta V. Okay? And as we have seen, both the bit line and bit line bar will be connected to the two ends of the sense amplifier. So let us see what is happening at the two ends of the sense amplifier. So the sense amplifier, which will be connected to bit line and bit line bar, soon we'll see that when you turn on the word line and all the read current starts flowing from PG1 to PD1, the discharge on bit line will show up at the input of your sense amplifier, but your bit line bar will not change. Remember, there was no activity happening in the PG2 or the right hand side of the branch. And as a result, this small potential difference in this sense amplifier. What was the sense amplifier? It senses small differences in voltage between the two terminals and decides whether bit line is greater or bit line bar is greater, and it pins the value to 0 rail or 0 logic rail. Okay, so this is the entire process of your read operation. This was a bit more complicated, so let me just give you a quick overview. What we saw was, by the virtue that you had VDD on bit line and bit line bar and the word line was asserted, there was a read current flowing only from PG1 to PD1. From PG1 to PD1. Why was this the case? Because the internal nodes were such that PD2 and pull up 1 were disconnected or they were off, and PG2 was also off because you were not meeting the condition of VGS less than VTH. The only two transistors which were in active condition was PG1 and then PD1, resulting in a read current. This read current was resulting in a discharge of your bit line, and this was picked up by the sense amplifier and pinned to 0. Okay, does that make sense? In the opposite case, if 1 was stored in storage node 1 and 0 in storage node 2, which will be the transistors which will be active? It will be, of course, be PD2 and PG2, just symmetric. It will be PG2 and PD2 if there was 0 on N2 and on N1 you had 1, right? And then what would have happened is bit line bar would have become VDD minus delta V, okay, in that scenario. And your sense amplifier would have read that your N1 has the value 1 and it would have pinned the value to 1 rail. Okay, the output would have become 1 rail. So this is the entire concept of your SRAM read operation. However, all these things do not ensure one very important condition, and that is what we will discuss in the next slide, which is how do you ensure that all of this happens without the alteration of N1 and N2. That is a very important consideration. Otherwise, SRAM cells will also will become like DRAM cells. You will have to refresh them after every read because it will become destructive read. But SRAM cells, the fundamental operation is it should have non-destructive read. So how do you make sure that N1 and N2 values are non-altered when all these dynamic processes happening? And this is what we will see in the next section. So very simple to see. In our previous example, all the activity was happening only in PG1 and PD1. So let us analyze that loop only. Remember, only active cells when you had a storage node N1, 0 and N2, 1 was PG1 and PD1. So let's look at what is happening at PG1. As we described, because there was an I read current, your voltage at Vn1 increased little from 0 to plus delta V dash. Okay, and this VDD was discharging from VDD to VDD minus delta V. Okay, what do you think should be the condition that you have a non-destructive read? It doesn't look like it is an absolute non-destructive read. Why is it not an absolute non-destructive read? Because the value for a small fraction of time or for a small transient of internal node N1 is not always at 0. It is becoming 0 plus delta V dash. But to ensure non-destructive read, at least we can make sure that delta V dash is very, very tiny. And what is the definition of tiny? As we have seen, it should be much lesser than the noise margin of your SRAM cell. And this is why the concept of noise margin becomes important, not only in storing information during the hold cycle, but also ensuring non-destructive read in the read cycle. And how do we ensure that this delta V dash is very tiny? It is less than the noise margin. And to do that, we will do a very simple analysis of these two transistors. We will abstract these transistors as simple resistors having some on-state resistance. So the on-state resistance in this case for PG has been retermed as R on of PG1, and for PD1 has been termed as R on as PD1. Okay, so if we look at the voltage divider circuit, you see that one end is VDD, another end is 0, and the storage internal node is 0 plus delta V dash. 0 plus delta V dash. So what will be the value of delta V dash? What we have seen in our basic courses, basic circuits courses, the voltage divider circuit, the value of 0 plus delta V dash or delta V dash will be nothing but the resistance of the pull down transistor divided by the total resistance, which is the summation of pull down transistor and pull up transistor. And to ensure that this is a non-destructive read, we should make sure that delta V dash should be very small. How do we ensure that delta V dash should be very strong? We should ensure that the strength of the pull down transistor should be much larger than the strength of the pass gate transistor. You can analyze this in two ways. Either you look at the formula and say that the resistance of the pull down transistor should be much smaller. That means the strength should be much larger. So resistance of the pull down transistor should be much smaller than the pull up transistor. Then only the delta V dash will be small, right? The other way of looking at is to see that the current or the drive strength of the pull down transistor should be much greater than the pass gate transistor. Okay, a very logical way to look at the same is, suppose there is a tug of war between guy PG1 and guy PD1. If I want to bring the voltage close to 0, which is on the other end of PD1, it is but obvious that PD1 should be the stronger transistor, right? Or it should have higher drive strength or lower on resistance, and this is the condition that we have mentioned here. As we know, the on state current of the transistor is proportional to W by L, and therefore we need to do appropriate transistor sizing between the pull down transistor and pass gate transistor. Since the drive current of the pull down transistor should be much larger, the W by L ratio of the pull down transistor also should be much greater than the W by L ratio of a pass gate transistor. Now, a practical consideration is, for a particular transistor technology node, generally the channel length of the transistors is fixed, right? That's why we say it's the 45 nanometer node or the 22 nanometer node or the 10 nanometer node. It is basically the channel length is fixed. Therefore, the only lever when we try to change lithographically through transistor sizing is generally the width of the transistor. For planar CMOS technology is the width of the transistor in planar CMOS technology, and when you go to FinFET technology, it is the W effective, which can be controlled by the number of fins, and that is something that we will see very soon. So therefore, because the L of the transistor is fixed, you have WPD greater than WPG to ensure that delta V dash is small, which is in turn to ensure that you have delta V dash within the noise margin, which allows for a non-destructive read. Therefore, the cell ratio is by definition the ratio between the W by L ratio of the pull down transistor and the pass gate transistor, and this should always be greater than 1. For advanced technology nodes, the value for cell ratio is generally between 2 to 3. So the width of the pull down transistor is generally 3 times that of the pass gate transistors, 2 to 3 times of the pass gate transistor. Therefore, we conclude that the read operation happens only from these 2 transistors out of this dense matrix of 60 SRAM cell. This is facilitated by the read operation, which causes a discharge on bit line and a slight positive voltage delta V dash on the internal storage node. But it is very important to have appropriate transistor sizing through the cell ratio for non-destructive read process. Okay, so we have discussed the non-destructive read process in this particular session. In the next session, we will see that how read happens dynamically through read timing diagrams. Let us meet for the next session.